morning everyone. This is Dr. Abhay Bhardwaj from KIET School of Pharmacy. Today we will dealing with the topic stereoisomerism of biphenyl compounds. That isomerism is also known as atropisomerism. Before going to understand about atropisomerism, we should know about which kind of molecule are generally dealing in that particular isomerism. So dear student, it is a biphenyl molecule. A biphenyl molecule is a molecule where the two phenyl ring number 1 and number 2 are connected to each other with the help of this bond, and this is a simple covalent bond by which both of the phenyl ring could be rotate any side. So dear student, if we will cut this molecule from the plane of symmetry, so that molecule will be equally cut into the two segments. That's why there is no any chirality will be possessed by the molecule, and the overall molecule is optically inactive. However, biphenyl with large substitution at ortho position, just mind this word, if we will substitute any compound or any substituent toward the side of ortho orientation of this molecule, likewise you can see here the OH group is attached at the ortho position of this phenyl ring. Same here, and the another phenyl ring is substituted with another second hydroxyl group here. So in both of the cases you can see the biphenyl ring is substituted with hydroxyl group, and at another and the bigger ring is a part of the another ortho substitution. So by which we can say here the molecule, just because of the presence of ortho substitution or any bulky ortho substitution, it will loses their free rotational tendency, and the free rotation of the molecule will be highly restricted over here. And once the molecule will comes under in a highly restricted rotation, that particular isomerism is known as atropisomerism. So here we have the example of polynuclear aromatic system where we are quoting the example of biphenyl. The two isomers are going form where the first one is showing the specific rotation around plus 35.5 degree, and another one is showing the negative same specific rotation, that is minus 35.5 degree. Now I am coming on the main mechanism, that is isomerism, which will be known as atropisomerism, which are generally coming in the molecule, or it is generally found in the molecule just because of the restricted rotation. So restricted rotation is only feasible when the specific position of the molecule will show the restriction. So in that example you can see the middle bond is carbon-carbon sigma bond. If I will just substitute some group A over here, that is the ortho position of this molecule. Same here, some another B molecule or substituent if we will add over here. So now if that molecule, if the both ring will want to be rotate, then again B and A will create some hindrance over there. That's why the free rotation will not be feasible in between the molecule, and the molecule will show the restricted rotation. So as per the atropisomerism isomerism, the number of isomers will form just because of the restricted rotation, and these isomers are also known as atropisomers. Okay, in the Greek language the atropisomerism means A means not, and tropos means turn. So basically there is no any kind of turn inside the molecule, or we can say in an elaborated word, any kind of rotation will not be possible. So basically biphenyl molecule is the main molecule which is showing such type of restriction just because of the substitution. So we have the example like enantiomers of the 6,6-dinitrophenyl 2,2-dicarboxylic acid. So dear student, 2 biphenyl are here, one is here, another one is here, and it is substituted with 2 big functional group, bulky functional group. First one is nitro, another one is the carboxylic acid. So just because of these 2 group, first ring, and same presence of 2 bulkier group on the next ring are showing the restricted rotation, and just because of that, if the position of these substituent will change, then the number of isomers as the atropisomers will form. So you can see the same molecule is showing the alpha and beta notation, and the different enantiomers are going form as a isomers. We have some conditions of atropisomerism where a rotational stable axis means, with a good example of biphenyl, there is a middle bit bond between the 2 rings, so it will provide a rotational axis, and once this rotational axis will be restricted, then the atropisomerism will be follow inside the molecule. The presence of different substitution on the both side of the axis, so it is a specific substitutions or the bulky substitutions which will be formed towards the ortho position of the biphenyl rings. The third condition is configurational stability of axially chiral biaryl compound. It means once the molecule will attain the ortho bulkier group substitution, then it will loses their achiral or symmetric character. That's why finally it will be treated as a chiral molecule towards both aromatic ring. So these all are the condition of the atropisomerism. So I think the topic will be helpful to everyone. Hope you will like that. Thank you everyone.